Hi there. So we're now looking at the last lecture that I have on substitution reactions, and I've titled it Checking Out the Scene. Play on words, checking out meaning that we're finishing with this section now, and just the acronym that we use, SCENE, to analyze our reactions. Now, this lecture we're going to basically look at 4 different examples and kind of unpack them using this. There's some stuff that we need to learn here, so this isn't just a whole bunch of examples. But what I want to encourage, though, is as I put each question down, is for you to just pause the video and then just attempt the answer yourself first, and then watch me as I unpack it a little bit more. All right, so the first example I'm going to write down is this. All right, so now's the time to pause the video and try and figure it out. Right, how did you do? Okay, so let's just draw out the answer for you, just to settle that in your mind if you got it correct. So the answer, this is a tosolation. So we're changing the OH into a good leaving group, and it is also actually a substitution reaction. So we're going to look at that now and analyze it in terms of this this acronym. So the tosolate, so the product looks like this. So we've got the stereochemistry, we haven't changed that. So we've got a TS over there. And that is the immediate product. Now I'm going to do something with that product next, but let's just have a look at this mechanism and analyze it in terms of our acronyms, the SCENE. I need to remind you again, you should remember this, but what does this tosyl chloride look like? So let's draw that out. Remember, it's paratoluene sulfonyl chloride. So it's the paratoluene, there's the sulfur over there, double bond oxygen, and a chlorine over there. Now, why is this actually a substitution reaction? In fact, I did this reaction in a previous video, and one of you, well, some of you might have actually thought, hang on a second, why did I do that mechanism in the way that I did it? Because what I did is I recognized, obviously, that we've got a leading group over there, and we've got a nucleophile over here. So what's the story? Well, first of all, when I did the mechanism, I didn't show the pi bond and the oxygen break. I just showed the nucleophile come in and the leading group leave. And that might have felt slightly odd, but you need to remember that the sulfur over here is actually sp3 hybridized. It's tetrahedral. It's a sulfur with 1, 2, 3, 4 things around it. It's a tetrahedral sulfur. And so the reaction is actually going to be a substitution type reaction. And we said that in the beginning with substitutions that we're looking at. Typically they were carbon, but carbon that was sp3 hybridized, which is tetrahedral. So this is the same thing over here. So let's just look at this in terms of things. So in terms of this reaction, do we have any sterics? Well, not really. In terms of the electrophile, the sulfur over here is got 4 things around it. The oxygens are quite small. The chlorine is small. We've only got one big bulky group on there. So really this is not a sterically bulky thing. So SN2 is kind of more likely. More importantly though, a carbocation, if this chlorine had to just leave, we get an S plus over there. And think about that for a moment. If it leaves and we get an S plus, we've got these 2 oxygens, which are more electronegative, pulling away. They're not stabilizing that sulfur in any way. So if there's a positive charge over there, the equivalent of a carbocation, that would be a sulfur cation, there's nothing that stabilizes that positive charge over there. Maybe a little bit from the benzene ring, but yeah, the oxygens that are pulling electron density away from that sulfur are really going to be destabilizing it. So in terms of carbocation formation, not so good. I would balance on the side that it's going to be an SN2. Then we look at the nucleophile. Now the nucleophile, of course, certainly changes things a little bit, because the nucleophile itself is not a good nucleophile at all. And that would normally, of course, be an SN1 type of reaction. Alcohols are not good. But the counterbalance to that bad nucleophile is that we've got a sulfur, a chlorine on a sulfur, and that is an absolutely excellent leading group over there. So as we add in, we can kick out that leaving group very well. So on the electrophile side, we're again very good. Then we look at the environment, and what do we have over here? So we've got a weak base, which does tend towards a little bit more to the SN1 side over there. We're not at any high temperatures, and the carbocation thing is really more important over here because it's not going to form, definitely not, unless we have some high temperatures here. So that's not kind of looking a little bit more on that side over there. We don't have a polar protic solvent, so that's looking a little bit more like that over there. So overall, this is feeling much more like an SN2 reaction, which is what it is. So mechanistically, we're going to take our lone pairs, we're going to add to the sulfur and kick out the chlorine in one step like that. Of course, once that reaction happens, we still have that proton over there, which needs to be picked up by the base, which will now be strong enough to pick up that proton, but only after we have added the sulfur to the OH over there. And it is important to remember, this absolutely is not going to deprotonate this before this reaction occurs like that. All right, so that was the first step over here. And now I want to do another step, because what we've effectively done is we have changed this OH now into a good leaving group. We can recognize that. That's something we can do even before we do the next reaction. So now I'm going to put the next reaction on, and I want you to try and guess what the product would look like over there. Well, guess, I mean, think through it logically. So the nucleophile I'm going to add is this alkynyl ether. So let's just put a methyl ether over there. And what we have over here is a bond to lithium. So this would be an ionic bond over here. So, okay, let's put in some solvents over here. I'm going to do this reaction. We'll keep it actually in DCM. And this is also done at room temperature. All right. Okay, if you come back, I want us to kind of work out this answer now before I just give it to you straight away. And I want to think about the thing. So again, we want to check out the scene here. We want to figure out, what sort of reaction is going to occur here in terms of substitution. Okay, so the S stands for sterics. Now over here, we've got a secondary, leaving group, and that is now it's still a little bit better for SN2, but SN1 is certainly a possibility. There's kind of like an even between them a little bit. So we really need to think about that carbocation. The carbocation that forms over there is a secondary carbocation, and that's not really great. All right, so we're certainly going to be along this side over here. In terms of the electrophile, we've got a good leaving group on it, so we've identified that there's nothing that really decides between with SN1 and SO2, just looking at this thing over here. In terms of the nucleophile, do we have a good nucleophile? And in terms of SN2 reactions, remember that the nucleophile that has a charge on it, so this is a C minus, is actually very good. In fact, this alkyne with a C minus over here is very reminiscent of the nitrile. It's exactly the same thing. It's a C minus with a triple bond, in this case an N. Over here, the triple bond goes to a carbon chain. So this type of nucleophile is actually really very much kind of promoting us towards looking like an SN2 reaction. And then we look at the solvent. The solvent isn't protic at all, so that's definitely looking like that. We see it's at room temperature. Room temperature is also a clue that we're more SN2-like. So we've got the solvents, we've got the temperature, and then in terms of acids and bases, we don't really have anything added on here. The nucleophile itself is in fact a base, so there's nothing more we can say with that. So SN2 looks like it's going to win the day over here, which it does. This is absolutely an SN2 reaction. It's going to win out. And so we can do this mechanism. So the mechanism, the electrons are coming from the carbon over here. This bond over here is a little bit more ionic than, we draw it with a line with the lithium to carbon, but is a little bit more sort of ionic. It could have been drawn as a C minus like we've done on a nitrile. That would have also been acceptable. So we come from those electrons over there, and we're going to add to this carbon here, and we're going to kick out the tosolate like that. And at this point over here, I want to just stop and I want to point out something very, very important. In fact, it is probably the most important reason as to why we need to talk about SN1 and SN2. Because this mechanism, this SN2 mechanism that's going to occur over here, remember how it happens. The nucleophile comes in and the leaving group leaves. And the nucleophile has to come in from behind the leaving group. And the consequence of that is that whatever is over here has to flip around to the other side. What that means is there's an inversion in the stereochemistry of this molecule. There's an inversion of the stereochemistry because the nucleophile came in from behind. When we draw it out, it needs to be showing from behind. So here's the product. I'll draw it here. Phenyl. And so the nucleophile came in from behind. It's a triple bond. And we get an OMe like this. So there's our nucleophile. I should have drawn it in and recognized it earlier on. That's the nucleophilic carbon that went in over there. And we had an inversion of stereochemistry. So as I've said, this is probably the most critical thing about an SN2 reaction and why we've had to look and piece together these two different types of reactions. When an SN2 reaction happens, the consequence of it is that there's an inversion of stereochemistry. In many cases, it doesn't really matter because, for instance, over here, this was SN2, but there was no stereochemistry on the sulfur. Two oxygens are identical to each other. So that sulfur, although it's tetrahedral, is not chiral. But we need to recognize SN2 reactions because this is what happens over here. Let's look at another example now. All right, here's the next example. So I encourage you to pause the video and work out what the product is. Okay, let's see how you did. All right, so this is going to be a substitution reaction as well. So we're going to look at this and let's just figure out what type of substitution reaction is going to occur. So the first thing that we need to look at is the sterics. Can we identify a leaving group and a leaving group and a nucleophile? Now the problem here is that if we look at this molecule over here, the alcohol over here is definitely the most nucleophilic, and then we've got a pi bond over here which is weakly nucleophilic. The lone pairs of the oxygen will be more nucleophilic, lone pairs always are, and so we've got a nucleophile over here, and then over here we've got HBr. And Br certainly looks like a good leaving group. So the question then becomes, well, hang on a second, how do we get this sort of reaction to go? So the issue here is that we don't see a conventional leaving group, and we actually really need to get to the E part, the environment, which is going to help us decide very quickly. So first of all, we are in a polar protic solvent and we're using heat. So we're definitely looking like we're on the side of an SN1 type of reaction. But the inclusion of acid over here, that this HBr being very acidic, is actually the big clue that we need in terms of what's happening in this reaction. Because the acid is going to create our electrophile. We've got this this bad leaving group over here, but the presence of a strong acid like HBr means that the OH is going to be converted into hydronium, making it into a good leaving group. And in the process of doing that, we now activate the fact that we've got this electrophile. Whenever we are forming like a hydronium, almost certainly at this point over here, we're going to be looking at an SN1. So I was very foolish over here. I've put those ones down there. What I meant to do was they should be there. All right. And so our electrophile is definitely pushing that way. The steric hindrance is kind of between, it's a secondary leaving group, so we're kind of sitting between the two of those. There's not too much that we need to consider there. But the carbocation is not just a normal carbocation, because if this leaves, we get a plus on the secondary position, which should not be good for carbocations. The plus is next door to an alkene, and that means resonance stabilization can occur. And that is fantastic. And that really is going to stabilize that carbocation a lot just like a tertiary carbocation, in fact, relatively speaking. And so we're looking at an SN1 type thing. And then the nucleophile, now that we've realized what's happening in the environment and this protonation, we've got a Br minus. Br minus is a terrible nucleophile, not good at all. And it also says that we're going to be doing something along an SN1 route over here. So this reaction must be SN1, and let's look at what happens over here. Now, it's going to be tempting to say that when the first step that we need to do is we need to protonate. So we're going to we change the thing into a leaving group. So I'll do that like that. And now we recognize that actually it was the bromine, which is going to be our nucleophile, and the acid over here is the thing that was important for creating that leaving group, like that. Okay, so we've protonated. Obviously, this would be in equilibrium because protonation is just something like that. When this leaves over here, we generate that carbocation. So we generate that over there, the carbocation. And the carbocation is a resonance intermediate between that and this over here. Those two are both valid resonance intermediates. Now, a key thing to remember, and I mentioned this is in an earlier video that was important about carbocations, is that carbocations are flat. Carbocations are sp2 hybridized, and that means that they're flat. And that means when the nucleophile comes in, so we've got our Br minus, which is the nucleophile, when it comes in, it can add either from the top of this carbon over here, or carbocation, or from the bottom. And so there's two faces that we can add from, and the choice here is essentially 50-50. So when we form this product over here, like that, we can't put stereochemistry at this position over here because it's going to have been destroyed. This will be racemic. So we put a plus and minus in front of it to say that it is racemic. Now, some of you might be looking at this and saying, okay, why does the bromine go there and why not to this carbon over here? Why can't it go to this carbon? And that is actually one of the sneaky things here. In fact, this reaction, what I've shown you drawn out of there, doesn't form very well at all. There's only about 20% of that gets formed. The major product in this reaction is actually where the bromine added to the primary position over there. So that was our nucleophile that went in. Of course, it's now become a good leaving group, but in the context of this reaction, how we've made that into a leaving group, it's been able to do that. So why does that happen? Well, this actually invokes another aspect of going back to when we're looking at the sterics in this reaction. Remember that this is not an equilibrium, all right? This is not an equilibrium. What this is showing us a picture which looks a little bit like this. There's a positive charge over a delocalized system over there. And the bromine, the nucleophile that's coming in, either is going to add to this carbon over here, which is more sterically hindered, versus this one, which is a primary carbon, which is more accessible. And so adding here is actually the preferred way. One way of doing that mechanism is to do it this way. So you show a Br minus going to that over there. Another way of doing the mechanism is actually just to say Br minus comes in, adds to this carbon, and this pi bond shifts across. Both of those mechanisms get us to the correct product over there. And both of them would be completely correct. There's nothing that says that we have to do it one way or the other. But the key thing in this reaction is that we've got to watch out. When delocalization happens, when we form a carbocation, we really have to keep our eyes and ears open to be and watching carefully about where that nucleophile is going to attack, because this can cause a bit of a problem and a bit of mixtures. It is one of the problems with SN1 reactions, which we need to look out for and predict. Okay, let's look at the next example. All right, here's our third example. Have a look at this and see if you can get the answer. All right, let's see how you did. So we need to analyze this again in terms of our acronym. So we write down scene and we ask ourselves the question, first of all, so can we identify the first bit is looking at the electrophile and the sterics and the carbocation stability of that. So over here is the one place that we can see a very clear leaving group bonded to a carbon. So that's looking quite good over there. And this carbon has 3 phenyl rings around it. That's pretty big. And so maybe we should actually just draw that out and have a look at what that looks like. So we've got, there's the chlorine, and we've got 3 benzene rings surrounding, those are not the best benzene rings I've ever drawn. So this carbon is clearly extremely sterically hindered. I mean, there's no doubt about this, that this must be an SN1 type of reaction. In fact, in earlier lectures, I've said that we do need to look at the whole scene in order to decide. But there are sometimes cases where there really is no decision to be made. When we have a tertiary leaving group, it has to be an SN1 reaction. We don't even need to look any further at some other things. So it's good to evaluate the whole system and setup, but a tertiary leaving group is absolutely going to be an SN1 reaction. It's just too bulky for a nucleophile to come in to do an SN2. If the chlorine leaves, the carbocation that forms is not only a tertiary carbocation, but it's stabilized by the benzene rings. It's a benzylic position because the carbocation is just outside the benzene ring, but 3 benzene rings. So this carbocation is a wonderful exercise in drawing out resonance delocalization, if you want to practice that, because there's so many places that the negative charge can be delocalized. It'll be 1, 2, 3, 9, 10 places that the positive charge will be delocalized. So like I would put 3 ticks for the carbocation. In terms of the electrophile, the leaving group, there's nothing we can really say too much about that. Chlorine, not a great leaving group, but either way, it's not really something we'd make a major decision between SN1 or SN2. The nucleophile, however, is a terrible nucleophile. It's an alcohol, absolutely is going to be an SN1 type of reaction. And I'm happy to put that there because in the environment, we've got a weak base over here, pyridine. Very weak base, nitrogen aromatic. Remember what pyridine looks like? It's the nitrogen equivalent of benzene. So this is a very weak base, pK of about 5. It's not going to pick up that proton over there, not make it into a good nucleophile. So we're definitely there. The environment also shows that we're warming things up a little bit over there. So that's also looking pretty good for being an SN1. Overall, this thing is SN1 all the way. And so what must happen is the chlorine needs to leave. We've identified that as the leaving group. We've identified this as the nucleophile, and it is going to have to then react with the carbocation. So we'll do that, and that reacts over there. And then the last step is the pyridine needs to pick up that proton over there. And so what we should get as a product is O, and then I can write CPH3, I don't want to draw it out. This, by the way, is also a protecting group that people use for alcohols and amines. It's called the trityl protecting group. It can be removed using hydrogenolysis. That's a bit more information for the second year course, but it's just another example of a SN1 reaction. All right, time for the last example. All right, here is our last example. Have a go at predicting what the product is, and then we'll discuss it. Right, so this one over here, let's just analyze it in terms of our acronym again, and let's figure out what happens. First of all, in terms of our electrophile, well, we've got a good leaving group over here, so this is looking fantastic in terms of the electrophile. The nucleophile is an amine. Amines are great nucleophiles. So let's look at this electrophile. is there any issue in terms of sterics? It's a primary leaving group over here. This is looking absolutely like it's favoring an SN2 reaction, carbocation formation, terrible. This would be a primary carbocation, absolutely not. So SN2 is looking absolutely excellent. Got a great leaving group on there. That's not really too much of a decision that we need to make. In terms of the nucleophile, we've got a neutral amine. We need to check that it is definitely a neutral amine, not an N minus. It wouldn't make too much difference just in terms of a substitution reaction. But this base over here, potassium carbonate, is not a very strong base, certainly not strong enough to remove a proton. Potassium carbonate will, in solution, get you to like about a pH of 9, I think, and no, 11. And so it's not strong enough for the 35 that we'd need to get the H being removed over there. So in terms of the environment, we are looking very much like we're going into an SN2 type reaction. The nucleophile is definitely looking like an SN2 reaction. Acetone is, whilst polar, it's an aprotic solvent, so that's looking like that over there. And we haven't been told the temperature over here, but certainly this reaction, I could have done it before. It wouldn't have made any difference to our outcome compared to this, what we've said over here so far, but room temperature is probably what we do this reaction at. Okay, so without a doubt, this thing is looking like an SN2 reaction. Good. Now, what is the product over here? So we want to work out what the product is. So it's a one-step reaction. This needs to kick in over there, kick that out over there, and so we would get this as the intermediate. So we've got our nitrogen. It's added to the two new carbons, carbon. The iodine was kicked off. We have two H's over there, so we can't forget those, which means that this is now positively charged. And then we have the base, of course. And so we've got CO2, technically 2 minus. Minus is on the oxygen. So one of those can pick up a proton like that, and we form the hydrogen carbonate. I can decompose. Again, the second time gives you carbon dioxide. And what we get is this product over here. Now it turns out this is highly unlikely to be the final product, and it's one of the real problems that we have with using nitrogen as a nucleophile, and while the precise reason why I've used this reaction. See, the problem is that the product, this is a primary amine and this is a secondary amine. The inductive effect actually makes secondary amines slightly more nucleophilic than primary amines. Not a lot, but there is an effect on that. And nevertheless, the big problem is that in this reaction, we've got a really, really good electrophile over there. And so what's going to happen, absolutely, is that it's going to happen again. It will react and kick out, and we'll get a substitution a second time. Moreover, we actually have a real problem in that it might even go a third time. Depending on how much of the starting material and how we control this reaction might actually end up forming a quaternary ammonium salt like that. And you can go and add that 3 times and see what happens. Amines in substitution reactions, particularly on a primary leaving group, are very prone to this type of thing happening over here. We can use amines in substitutions, but we need to be very careful about watching out for this. This type of reaction is just extremely difficult to do. You might be able to control a little bit if you control the equivalence and the temperature, but one still has to be careful with it. What is more likely to work, though, is when you react an amine with a secondary leaving group. So if we've got a secondary leaving group, R and R1, so here the leaving group might actually be, so this would be a chiral sort of leaving group. So that could have been bromine or iodine, anything we've had before. If we do that, we've got a better chance of us doing what we call a monoalkylation, where the alkylation has happened only once when we use a primary amine. There's still a chance of the secondary alkylation, but it is lessened because of the sterics of this reaction. So the secondary one is more sterically hindered. So that gives us a little bit of a boost over there. But certainly if we use a secondary amine, so maybe something like pyrrolidine, which we've used before, so we need to have some kind of base to pick up the leaving group and the proton that needs to go. With something like that, we can get a substitution occurring. It's again SN2 reaction, and we could get a substitution that would work like that. This tertiary amine is going to be very sterically hindered to react now with a secondary leaving group alkylating agent over here, which is our electrophile. And so that type of reaction is likely to work, and that'll be fine. But using an amine on a primary alkyl halide or alkyl leaving group, something like that, is going to be problematic if we just wanted to get on going once. And so for that, it's sometimes better to maybe do a reductive amination, which we've discussed in a previous lecture, as a way of trying to prevent that. But even those reductive aminations, if you're not doing them carefully, could also happen twice. Okay, so this finishes off our lectures on substitution. Hopefully that's been kind of informative. Our next lecture is going to really kind of throw everything on its head, and we're going to have our wits about us. We really need to understand our substitution reactions well, because we're going to now move into an alternative, and the alternative is called elimination, and it really is the opposite of substitution, and yet we're going to see the conditions sometimes look very, very much the same, and so we're going to have our wits about us when we study that. Good. See you then.